Hi everybody, thank you for coming. So we'll continue today. We'll talk about message integrity and message authentication. All right. So let's see what we're gonna cover today. All right. So let's talk about message integrity. The cryptography system that we have studied so far provide secrecy. Data is encrypted. That means it's private, it's secret, nobody can read it before decrypting it. So all we provided is secrecy or confidentiality, but not integrity. Okay, not integrity. So it could be in secret, but somebody had altered it, changed it, right? So however, there is actions where we may not even need secrecy, but instead must have integrity. As I told you, example, if there is no class Thursday because there is snow tomorrow, so this message does not need to be secret, does not need to be encrypted. However, it needs to be integral, authentic. All right, you need to make sure it's coming from me to you. It's not somebody trying to fool around sending you this message, right? So that's what is integrity. Is how to make the data integral. All right, so we're going to talk about document and fingerprints, message and message digest, the difference between them, checking integrity, cryptographic hash function criteria. We're going to talk about hash functions, which is very important for the message integrity. So let's talk about the one way to preserve the integrity of the document is through the use of fingerprint, right? When you write a document, if you need to make it authentic, what you do, you sign it, right? That's what you do, you sign it, right? When you write a check, so how can you know it's coming from you? By signing it. When it goes to the bank teller or the bank, employee, try to compare your signature there with the signature on that paper. All right, fingerprint. So if Alice needs to be sure that the contents of her document will not be changed, she can put her fingerprint at the bottom of the document. That's real life, right? So the message and message digest. We have to, what we do in the practicality in the digital world, we create something called digest. Digest is a small. Okay, so the electronic equivalent of document and fingerprint pair is a message and digest pair. So what you do, you have a message, you're going to have one hash function, there's many of them, we're going to discuss them next class, hash functions, okay, and you create a message digest. So usually the message could be any length, however the digest always fixed size, alright? So that's what we create using this function. We create the digest, or we call it fingerprint, or whatever you want. Alright? Okay. And you attach the digest as you are attaching your signature in real life to that message. When the receiver receives this message with the digest, what he has to do? Try to calculate the digest again. If the digest equal to the one received, then the data is, or the file is, authentic, integral. If it has changed, that means it's not integral, right? As simple as that. So there is no talent. Where is the talent in here? In the hash function. So the two pairs, document fingerprint and the message digest, are similar with some differences. You agree? That document and fingerprint are physically linked together. The message and the message digest can be unlinked, could be sent separately, or could be linked, sent together, okay? And most importantly, the message digest need to be safe from change. Right? So the message digest needs to be safe from change. So what will happen in here? So you have your document, for example, you apply a hash function to generate at the gist, alright? So, okay, so that's at the receiving side, right? You received it, okay. So that's the previous digest received. If they are the same, then message is not changed. If if the digest, the received digest and the calculated digest are not the same, then the message is changed. Throw it. Don't use it. So if you receive a message from me telling you you have no class Thursday, please do that, right? Make sure it's coming from me. Make sure it's an authentic one. All right. So let's talk about the cryptographic hash function criteria. All right. So what is the magic in here? Where is the talent in here in selecting what? The hash function. So the hash function has to have a criteria, different criteria to make it strong. So a cryptographic hash function must satisfy 3 criteria. Preimage resistance, number 1, I'm going to explain. Second, preimage resistance, and collision resistance. Preimage, second preimage, collision resistance. So this is a cryptographic hash function criteria. How many? 3. Preimage resistance, second preimage, collision resistance. All right. So what is a preimage resistance? I'm sure you're kind of sensing it. So preimage resistance. So for example, if you are given y, which is, and you're given a message m, you do the hash, you're gonna get y. So the preimage attack that you could find any other message such that y equals hash of the other message. So in here you have a message and other message, both the hash function gave you y. That is not good. That is not good. So for example, take a look in here, the preimage. Okay, so that's a preimage. So that means the hash function, if there is 2 different messages, should not give same hash function. All right. So in here, for example, if the message m, your message is m, the hash, which is a hash function, h, right? And the hash of m will give you a digest. Alright? Digest. So you pass the message to the hash function, will give you the digest. What is the value of the digest? Y, which is equals applying the hash to the message. Right? That's Alice. Alright? In our all examples in this book, Alice is a good woman, Bob is a good man, Alice sending to Bob, and Eve is the bad woman, okay, the bad person. That's right? Alright, so it's sent to the good Bob, right? So good Alice send it to good Bob, right? What will happen in here if Eve gets the hash, which will get the hash, because the hash is sent over the network, right? And if she can get another message, okay, that produces the same hash, all right, she could send the wrong message to Bob, and Bob what will do? Will calculate the hash again. What's the value of the hash? Y, which is a correct hash, but the message is wrong. All right? So the preimage is a problem. So given y, find any m prime that is y equals hash of m prime. Alright. So that will be a problem and Eve will win. Alright, so that's a preimage. So the question here, can we use a conventional lossless compression? You know compression, there's 2 kinds of compression, lossy and lossless, right? Lossy, when you compress, you cannot bring it back as it was. You could, alright, perfectly as it was. Lossless, you don't lose anything. You could bring it back. So there's lossy, there's lossless, right? That's a compression science, right? Such that stuff it as a cryptographic hash function. What do you think? Lossless. Maybe not, right? So we cannot. A lossless compression method creates a compressed message that is reversible. So we don't want to have the message digest is reversible. So we could go only from the message to the digest, but we cannot go from the digest to the message. Alright? So another example. Can we use a checksum function as a cryptographic hash function. You know what checksum in communication, right? Right? You took it in DCC, right? Checksum, right? Can we use it? What do you think? You don't have to think, we cannot, right? Why? The checksum function is not a pre-image resistant. Eve may find several messages whose checksum matches the given one. It's not a pre-image resistance, right? So you could have message 1, message 2, message 3, message 4, all of them will give you the same checksum. So it's not pre-image resistance. Okay, so that means the message has multiple images could give the same hash. So it cannot be used. Okay? Alright. So second pre-image resistance. So second pre-image attack in here. So if you have given M and hash of M. So if Eve knows M, what is M? A message. And in our case in here, it's not a secret. Everybody knows the message. I don't care about hiding the message. I'm just caring about make sure it's authentic, right? So Eve could have the message and the digest, which is transmitted in the network, right? So what the attack? Find M prime, which does not equal M. You don't have to find M, the message, different M, such that the hash of M and the hash of the M prime are equal. Alright? So you're starting from knowing the message and the. So in here what will happen, again, the message hashed, this is the digest, alright? You combine the message with the hash. That's how it is, that's how you send it. Now Eve received the digest and the message, tries to find another message prime that will give you the same hash, the same digest. Alright? What she will do, okay, instead of sending the right message, it will put the fake message with the digest to Bob, to the good Bob. Bob receives it, checks the digest, it's good. Okay, it's good. Alright? So, but that's a problem. So, given M and HM, find M prime, that M does not equal M prime, but the hashes are equal. This is the second pre-image attack. It's bad. So, any function, any hash function we use should have second pre-image resistance. Okay? Resistance. Then you have collision resistance. So given none, you have none. Okay, so you find two messages, the real and the M prime, such that H of M, okay, this is by collision. Just happens, collision, collision, it happens, right? Okay? So in here, what will happen? That you have a message, you could have two messages, and they could collide that both produce the same digest, okay? Alright, so we are talking about hashing function to create a digest. There is multiple hash functions, we're going to talk about them next time, complex, some of them are very complex, okay? But the random oracle model, which was introduced in 1993, okay, is an ideal mathematical model for a hash function. So let's talk about ROM, alright? So we're going to talk about Pigeonholed principle, Pigeonholed. Anybody likes pigeons? Anybody like to eat pigeons? No? Nobody eats pigeons here? Alright? And like to have pigeons as pets? No? Used to? Yeah? Did you use them for messaging?
No.
No? Yeah. Then we'll talk about per day problems, and we'll talk about attacks on the random oracle model, attacks on the structure. Alright? So let's take a look at this example. Assume an oracle with a table and a fair coin. The table has two columns, so the message and digest, right? Usually the message could be a variable size and the digest is a fixed size, always, alright? So look in here, this is three messages in here, produced three different digests, okay? Alright, so the message AB1234, okay, whatever is given for digest calculation. This is a message given for digest calculation. The oracle checks its table. You're gonna check the table in here. It's not. Do you see it in here? It's not there, right? Okay. Okay. How about here? The message for
Yes, the first one.
the message for 523AB, okay, which is this one, is given for digest calculation. The oracle checks its table and finds that there is a digest for this message in the table, first row. The oracle simply gives the corresponding digest, which is 103A AB, right? AB. In the oracle example in the previous one, cannot use a formula or algorithm to create the digest for the message. There is no formula. There is, kind of random, right? Alright. So like a table lookup. For example, imagine the oracle uses the formula HM equals M mod N. So that's the formula. That's how you create the digest. You take the message, okay, modulo N. Now suppose that the oracle has already given HM1 and HM2. If a new message is presented, let's say M3. M3 equals to M1 plus M2, right? M1 plus M2. The oracle does not have to calculate the M3. Why? Because it just has the digest of M1 and the digest of M2. You don't have to calculate it. If you have the digest of M1 and the digest of M2, just add them up and mod N. Okay? So for example, hash of M3 equals M1 plus M2 mod N. M1 mod N plus M2 mod N equals the hash M1 plus, okay, so you don't have to calculate it. This violates which one? This violates the third requirement that each digest must be randomly chosen based on the message given to the oracle. So this is not a good algorithm. This is not a good algorithm. Okay? Because you could relate two messages to each other. And this avoids the third condition, which is collision resistance. Collision resistance, right? So, any questions so far? Take a look at pigeonhole principle. So what is pigeonhole principle? If we have like 6 holes and 7 pigeons. Okay, so how many holes will have at least 2 pigeons? 1, right? And that's a problem. The problem is the size of the message is big and the size of the digest is small. So there is very much likely that you'll find for each digest a lot of messages, right? A lot of messages. So if n pigeonholes are occupied by n plus 1 pigeons, okay, then at least 1 pigeonhole is occupied by 2 pigeons. What we're trying to say in here, that there is a possibility that you'll have 2 digests for one there is 2 messages for one digest. So think about the digest in here as a whole, and messages as pigeons. All right. So why? Because the size of the pigeon, the size of the message is much bigger than the size of the digest. So the generalized version of the pigeonhole principle is that if n pigeonholes are occupied by kn plus 1 pigeons, okay, kn, then at least 1 pigeonhole is occupied by k plus 1 pigeons, right? So if you have kn plus 1 pigeons, okay, so so you have n pigeonholes, okay, so each pigeonhole has how many? K pigeons, except one has k plus 1, right? I have n holes, okay, I have n holes, and each pigeonhole have k pigeons, but I have the total number of pigeons is not, you know, it's like kn plus 1. So one hole will have k plus 1 pigeons. Okay, that's a general rule. Okay, so assume that the message in the hash function are 6 bits long. So how long is the message? 6 bits. So how many options we have with 6 bits? 2 to the power 6, which will give you 64, right? 64, right? 64 different options, right? 64 different options for messages, right? If I have 6 bits, if I have 6 bits, right? Okay. 0, 0, 0, 0, 0, 0, 0, okay, then 1, 0, 0, 0, 0, 0, then 1, 0, 0, 0, 0, 0. Alright, so how many are you gonna have? 64 different messages, right? Alright. So, what is it? So, 6 bits long, and the digest are only 4 bits. So how many options I have for the digest? 2 to the power 4, right? Which is 16, right? So I have for the 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0. Okay, and this how many? 16 options, right? So always, so if I have 64, each one will generate a digest. That means each digest, how many messages could have? 4, right? If I have to map one digest to every message, so that is 4 messages will have the same digest, and that's what is collision, right? You agree? All right. So 4 bits long. So then the possible number of digests is 2 to the power 4, 16, and the possible number of messages is 64. That means n, which is what is n? In the holes, is the whole 16, and kn plus 1 is 64. So k is larger than 3. K is larger than 3. The collision. The conclusion is that at least one digest corresponds to 4k plus 1 messages. Alright? Make sense? Right. Alright. So when you go to the per day problem, there is something called per day problem. Okay, it's a statistical model. So in the problem 1 in here, So there's 4 problems. Problem 1, 2, 3, 4. So if you in problem 1, it's what is the minimum number k? So what is the minimum number k of a student? So this is a students, right? Set of students. Okay, and we're looking at their per day. The per day, just the year. Okay, the per day. Okay, all right. So this is a set of students, right? And there's a predefined value. So in the problem number 1, it says, okay, what is the minimum number k of students in the classroom such that it is likely that at least one student has a predefined per day. So you put a predefined per day. What is the likelihood of having one student having the same predefined, okay, per day? The problem can be generalized as follows. We have a uniformly distributed random variable with n possible values. So you have n possible values from 0 to n minus 1, or from 1 to n possible values in here, right? What is the minimum number of instances k? What is the minimum number of instances k? That it is likely that at least one instance is equal to the predefined value. Right? So you have a randomly distributed, the students have different dates. Okay, what is the possibility that one student will have the predefined value will be presented in here? Okay, it's greater than 50%, as you see in paper. Okay. So problem number 2 in here, we don't have a predefined. In here, what is the probability that 2 students will have the same per day in the set? Okay, so let me read it for you. What is the minimum number k of students in the classroom that is likely that at least one student has the same per day of a student selected by the professor? So professor selects a student. What is the likelihood, okay, to have another student with the same per day? So for example, myself, I was born, for example, in we're talking about the day, 1st of the month. How many of you born in the 1st of the month? That's the whole question. All right? Right? This problem can be generalized as follows. We have a uniform distribution random variable with n possible values. What is the minimum number of instances k such that it's likely that at least one instance equal to the selected one? All right. Problem number 3. Okay. What is the minimum number k of a student in a classroom such that it is likely that at least 2 students have the same per day? At least 2 students have the same, okay, per day, any per day. So in here, predefined from outside. This is a predefined from inside. Okay. So this is from outside. You don't know anything about it. So you say 3rd. And here you have a student. It's 4th. You want to match it with another person has the 4th day. In here, okay, it's any numbers, right? Any to match it without a predefining, right? Okay. The fourth problem in here, okay, we have 2 classes, each with k students. So we have k students in here and k students in here. What is the minimum value of k so that it is likely that at least one student from the 1st class has the same birthday of the student 2nd one? So, for example, I am 1st, born in the 1st. What is the likelihood the next class next to us we have a student that's born on the 1st? Alright? Alright. So in here this is a probability. I mean this probabilities, and you find in the probabilities and statistics, you know, if you look at the I'm not sure if it's in here. Yeah, in here. So the summary of the solutions, you don't have to worry about the solutions, how to solve the probabilities, and okay. So summary of the solution to these problems are given in the appendix E. You could read it. So for problem 1, okay, the probability is P equals 1 minus EK over N. What is N? The total options. What is K? The number of instances. The number of instances. So the general value for K, okay, what I'm looking for K, right? I'm looking for a K. How many instances could happen? K. So if I solve this problem, that will get K equals this. Just okay. For the P, if I fix P to 50%, okay, that will be the value of K. So K, for example, in the first problem, what was the first problem? It's just refresh your memory. If you have a predefined per day, okay, how many K in the class will match? Okay, for 50%. So how you calculate it? Very simple. You're gonna know the number of the students, the number of your incidents, students, and multiply it by 0.69. All right. From here, to have a more chance for K, N has to be big. So in here we have 16 students, right? It's log. If we have like 500 students or 1,000 students, K will be higher, right? Okay, so in here, the number of students, let's say the number of students is 3065. So what is the chance for the first problem? Again, if you have a predefined birthday, let's say the first. I was born on July 1st, okay, July 1st, first day. And we have 365 students in here. What is the chance, okay, with 50%, I'll find instances like that we have the same birthday. If you use this formula, it will be 253. All right? And so on and so forth. This is the second problem, the third problem. That's what does it mean in the table. Okay, that's what does it mean in the table. Clear? Clear? Alright, so you see in here the graph for 4 per day problems. In here, first and second problem. Okay? And this is the third problem, this is the fourth problem. Alright? So K increases, okay, increases as the probability increases. So for example, for a probability of 50, okay, K in the first problem is much more less than for the second problem. Okay? Let's take the attacks in the model. What kind of attacks we could have in the model? Okay. So, preimage attack. So for I equals 1 to K, create the message of I. Okay. Then say, then create the message of I. Then create the hash, okay, and save it in the temporary digest. If the temporary equals to the digest, return MI. So the difficulty of a preimage attack is proportional to 2 to the power n. 2 to the power n. That means the higher the n, okay, the more difficult. The higher the n, the more difficult. Alright. So a cryptographic hash function uses a digest of 64-bit. How many digests does Eve need to create to find an original message with a probability of 50%? Alright. So again, what we have in here, we have a digest of 64-bit. How many digests? Okay. How many digests does Eve need to create to find an original message? So from a digest, how can I go to an original message? So the number of digests to be created, okay, equals K which is 0.69 times 2 to the power n. Okay, where is the 2 power n? What is n? Is the number of bits, right? So 64 option, right? To the power n, all right? So it will, that will be the figure. This is a large number. This is a large number. So Eve, even Eve can create 2 to the power 30. 2 to the power 30 is how much? 2 power, how much?
Large register.
So 2 to the power 10 is 1,000. 2 to the power 20, 1 million. Okay, 2 to the power 30, 1 billion. It's 1 billion, approximation, right? 1 billion. So message per second, if she has a fast computer that could create 1 billion messages per second, it takes the remaining, so 30 minus 64 seconds, which is 500 years. It's gonna take 500 years to be able to create every digest, okay? This means that the message digest of size 64-bit is secure with respect to pre-image attack, but as we will see shortly, not for collision attack. All right? You understand the point in here? The point in here is for a pre-image that's gonna take 500 years to create 64-bit. Still, by the way, a hash with 64-bit is a very weak. I mean, very weak. I mean, the minimum nowadays is 512. All right? So for the second pre-image attack, the difficulty of the second pre-image attack is also 2 to the power n. So if I apply the same thing, it will take that long. The difficulty of a collision attack is proportional to 2 n over 2. Much weaker. The first two first pre-image and the second pre-image is 2 power n. Now this is 2 to the power n over 2, much weaker. All right. So for example, if I go to the example in here, so that means this is what it will be 32. 32. Okay. That means this it will be how much? 2. Okay. 30. So you get 30, remove it from 32, how much remains in here? 2. That means how many seconds you need to crack it? Much faster. Right? Clear, or I have to, I mean, ask me, it's not clear, right? It will be much more, it will be much more, okay? So in the previous one, it's 2 to the power 64. If I can create 2 to the power 30, that means I need how many seconds? 2 to the power 64 minus 30, which is 2 to the power 32, right? In the second case, it's 2 to the power 64 over 2, which is 2 to the power 32. If I have a speed 2 to the power 30, that I need how many seconds? 2 to the power 32 minus 30, which equals 2 to the power 2. Right? Anyways, so a cryptographic half function uses a digest of 64-bit. How many digests does Eve need to create to find 2 messages with the same digest with a probability 50%? So the number of digests to be created is 2 to the power n over 2, right? Okay, 60. So 32. This is 2 to the power 32, by the way. This is a power, right? 2 to the power 32. So if Eve tests 2 to 20, okay. So how many seconds she needs? 2 to multiply to 2 power 18. 20 minus 32, 12 seconds, which will be 2 hours. 2 hours. So you could crack it in 2 hours. Okay, so this means that message digest of size 64 bits is not secure against the collision. Alright, so the difficulty of alternative collision attack is 2 to the power 2 to the power n. Alright, so that's what we conclude in here. Alright, the levels of difficulty for each type of attack. Preimage is order 2n, second preimage 2n, collision 2 to the power n over 2, alternative collision 2 to the power n. Alright? Same example. So let's take example with MD5. We're gonna study it next time, it's class. MD5, one of the hash functions. Alright. Which was one of the standard hash functions for a long time. Creates digest of 128-bit. That's the size, 128-bit. To launch a collision attack, an adversary needs to test 2 to the power 64, which is 2 to the power 28 over 2. Right? Tests in the collision algorithm. Even if the adversary can perform 2 to the power 30, which is 1 billion operations per second, it takes about 1 billion seconds or much more. It's like, 8 billion seconds, more than 500 years to do that, right? So MD5 is secure because it's a long hash, all right? For SH1, okay, it's 160. The length of the hash is 160. Of course, it will be much more stronger. Anyways, okay. Also, there is a taxon structure. The adversary may have other tools to attack hash functions. One of these tools, for example, is the meet in the middle attack. Let's take a look at message authentication. So a message digest does not authenticate the sender of the message. To provide a message authentication, Alice needs to provide a proof that it is Alice sending the message and not the imposter. The digest created by the cryptographic hash function is normally called modification detection code. So you need so you want to prevent from modification. All right. What we need for message authentication is message authentication code. Let's take a look. Okay. So in here, for example, so modification detection code. So you have the message, you have the hash, you created the modification detection code. Okay, modification detection code. All right. So what you'll do, you'll send the message in secure channel, and you have to send the channel in immune channel. You have to send the digest in the immune channel. So what will happen in here? You receive the message. Both know what the hash function is used. They create the hash, then you create the MDC, which is in here. MDC. Okay. The MDC received with the secure channel will be compared. If they are the same, it will be accepted. If they are different, it will be rejected. So in here, in the modification detection code, we have two channels: secure channel for the and secure channel for the data, and secure channel for the digest. All right. For the message authentication code, what we do, focus on here. There is a key in here. So to remove the need for secure channel, we added a key. So what we have the message in here. Okay, it will be hashed using a key. The key is a shared key, is a symmetric key. So both have the same key. We use it to create what? The digest. Alright? So now what we have, MAC, message authentication code. We call it MAC, message authentication code. Now when we send the data, we send them together, message plus the MAC in secure channel. And here we have to have a secure channel. In here we don't have to have a secure channel. So it was received. So what we have the message and the MAC. The MAC was created by what? By a key shared between the sender and the receiver. So we take the message, because both know the key, we'll create the MAC again, and we'll compare the received MAC with the created MAC. If they are equal, then the message will be accepted. Alright? So there is a difference. Again, there is a difference between message authentication code and this one, modification detection code. Alright? So in here we needed two channels, and here we needed one channel, but we needed also to use a shared key. So the security of a MAC depends on the security of the underlying hash algorithm. Okay? So if you have a complex hash algorithm, it will be. So you could have multiple versions. So for example, you could have nested MAC. So in here you have the message, you concatenate it to the key, you hash both of them, okay? Then you're gonna have the MAC and you send the key, okay? And you hash it and you create the final MAC. So in here, like nested, it's like, you know, nested. You created like, you did the hash a few times. Now at the other side, they will do it in reverse. They start from here, then you go back to here. Okay, that we call it nested MAC. In here, something called HMAC. Okay, HMAC. Which is the hash MAC, a different flavor, hash MAC. So in here, what you have, okay, you start in here, you divide the message. The message is divided in blocks. Okay, okay, M1, M2, M2. Okay, you combine them together. All right, and then you add B bits, and there's I pad, and add it to the B bits. So it has to be a multiple of the size of the B bits. So if it's not the multiple, you add like kind of padding in here. Okay, padding. To be a multiple, so to multiple blocks like that. So the iPad with the bad to the B function, then you create a hash, okay? Then you can bad it to the B bit and the output bad. So B bad, the B bits. So in here the hash will create N bits. So intermediate HMAC, bad it to the B bits, you're gonna have from this side and from this side, and then you hash it again, and then you create HMAC. Just making it more complex, right? So in this process, what you have a very long block. The block has to be divided into small blocks. These small blocks has to be equal. If they are not equal, you have to do padding, assemble the padding, and you do the whole process. This is the HMAC. There is CMAC in here, same thing. Okay, CMAC in here, so you have the message divided into blocks. And what you do in here, you have this stuff with the key. So you take the first block you encrypted, and you make it input for the XOR for the next one. Okay, and keep going until the last one. Okay, you select in leftmost bits, and that will be your CMAC. Okay. The bottom line, without the details in here, what you are using in here to do CMAC and HMAC, that you're gonna have a shared key. You're gonna have a shared key, and this to make the process much more complex, and then harder to regenerate.
Yeah.
So it's like, you know, you could go from a message to the hash, but if you have the hash, you cannot go back to the message. Okay, that concludes our class today. Thank you.